Hello, I'm Dr. AJ Kumar, PhD. This is Abstract Algebra. I'm not sure which video. We're reading section 2.4 of Artin, which is cyclic groups. I was just I don't know if I'll put the video up. I started trying to record an OP-HTTPD video over here and went through here. I started just making a list of all the books I want to read, and I'm just like, oh my god, look at all these books I want to read, and realizing I just have no chance of ever doing that, if I ever like skip a day. So you got to just start reading. Anyway, so we're going to read Algebra by Artin. Alright, and I probably cover my weak points. That's what I'm going to focus on, covering my weak points. My weak points are... Oh my god, I just thought of another book. Data mining... by Garwal. I think this will be a priority. For a variety of reasons. Basically, that's just a thing I need to learn how to do quickly. And then learning about like machine learning stuff. And I'm going to have QA and I'll be able to do this stuff. That's my idea. Okay, currently reading in the reading playlist. Currently reading on my own. Priority. Okay. Algebra. Okay, let's get to algebra. Okay. We now come to an important abstract example of a subgroup, the cyclic subgroup generated by an arbitrary element x of a group G. We use multiplicative notation. The cyclic subgroup H generated by x is the set of all elements that are powers of x, right? This is the smallest subgroup of G that contains x and is often denoted by brackets x. But to interpret 2.4.1 correctly, we must remember that the notation x to the n represents an element of the group that is obtained in a particular way. Different powers may represent the same element. For instance, if G is the multiplicative group R star and x is -1, then all elements in the list are equal to 1 or to -1, and H is the set 1, -1, right? There are two possibilities. Either the powers x to the n represent distinct elements, or they do not. We analyze the case where the powers of x are not distinct. Okay. Let x be the cyclic subgroup of a group G generated by an element x, and let S denote the set of integers k such that x to the k is equal to 1. The set S is a subgroup of the additive group Z+. The set S... Okay. Okay, this is the proposition, okay. Two powers, if x to the r is equal to x to the s, and r, number theory book, just remembered. A number theory book. I have one in mind, but... Greek philosophers, so Socrates, but all these Odyssey, Cicero. Jesus Christ, I have so much to read. Okay. 2 powers x to the r is equal to x to the s, with r bigger than or equal to s, are equal if and only if x to the r minus s is equal to 1, i.e., if and only if r to the r minus s is in S. C. Suppose S is not the trivial subgroup. Then S is Zn for some positive integer. There's two trivial subgroups. Then S is Zn for some positive integer n. The powers 1x x squared up to xn minus 1 are distinct elements of the subgroup brackets x, and the order of brackets x is n. Okay? Okay, for part A, if it's a subgroup of the additive group, so he's going to prove that it's a subgroup, I guess. If x to the k and x to the l is equal to 1, then x to the k plus l is x to the k times x to the l, which is 1 times 1. This shows that if k and l are in S, then k plus l is in S. So the first property for a subgroup is verified. Also, it's 2.3.1. Let me look that up. Okay, I'll just tell you where it is so that you can look it up in your book. There will be a link to buy this down in the description. This is page 43. This is page 43. Okay, so he's going to verify closure, identity, and inverses. Those are the properties. And so he just verified closure. Right, and here's identity. Yeah, so and here's inverses. There we are. Okay. B. 2.2.3, what's the cancellation law? Let me find the page for that. That is page 41. And that's if like AB equals AC, then B is equal to C. That's this implication. It's that type of implication, but x to the r times x to the s so we can just multiply both. So if we have x to the r, maybe I need some space. If x to the r is equal to x to the s, x to the s, then we can multiply both sides by x to the minus s, and then we get x to the r minus s is equal to 1. And likewise, if we have this, we can multiply both sides by x to the s in order to get x to the r is equal to x to the s. So the implication goes in both directions. Okay, this was correct. Okay, and then 3c. Okay, let me just. Okay, I'm going to get my highlighter, and in blue, highlight. Maybe this is what I should do: is go through here and highlight all of the prior references. Okay, this is the way I typically read a book. Is go through, highlight all of the prior references, and then find their page numbers, and maybe write them on a separate piece of paper. And then I will also highlight the terms, but let's do the prior references. Okay, we did the prior references. Let's do the terms now. Let's highlight the terms in yellow. Okay. Cyclic subgroup. And this was a prior reference. I'm going to make this bigger. Prior reference. No, I don't like that. That's too big. Middle. Prior reference. This is the cyclic group of order n. This is a term. It goes in yellow. Order n. This is a term. Infinite order. That's a term. Infinite cyclic. To generate the Klein-Viertelgruppe. I'm sure I butchered that pronunciation. Quaternions. Yeah, these are important. I'm going to put a star next to this because this group is really important. Star for important. These are from the Pauli matrices. All right, let's go walk through this again. Okay, theorem 2.3.3. Let me walk through and denote where all 2.3.3. Where's that? That is page 44. I'll just use this. Page 44. What is this? This is that every subgroup is one of these. Every additive subgroup. Subgroup of G of Z is one of those. That's what 2.3.3 says. And then, okay, 2.2.7. That is the usual presentation of S3. And 1.2.16. What page is that? Oh, 2.2.7. I meant to get the page number. Let me get that. It's page 42. One point 2.16. It's page 15. Or any other ones? Okay. And what does this say? This is that in this context, what is important about it? Yeah, it's that the elementary matrices generate GLN. That is basically, that's a consequence of 1.2.16. That's a consequence. Okay. Yeah, it says let A be a square matrix. The following conditions are equivalent. A can be reduced to the identity by a sequence of elementary row operations. A is a product of elementary matrices. A is invertible. So yeah, that makes sense. Okay. Let's go back and start reading again. Okay. Suppose S is not equal to the trivial subgroup, so just 0. Then S is equal to Zn, where n is the smallest positive integer in S. If x to the k is an arbitrary power, we divide k by n, writing k is equal to qn plus r, with r in the range 0 less than or equal to r less than n. Okay. Then x to the qn, right, then x to the k is equal to x to the r. Okay. Yeah, because it just cyclically goes through those powers. Yeah, and this is the well-ordering principle. Yeah, so there's a hidden thing here, which I think is, I guess, equivalent to the fact that you can do induction, which is called the well-ordering principle. And he may have proved this underhandedly, which is that every non-empty subset of the positive integers I'm just going to write it as integers, has a least element. That's the well-ordering principle. Okay. This group described by part C is called the cyclic group of order n. It is called cyclic, but because you just cycle through the elements. An element x of a group has order n if n is the smallest positive let me underline that, positive integer with the property, which is the same thing, okay, yeah, so an element has order n and the group has order n. So there's group order and element order. And these are different concepts. Okay. With the usual presentation of the symmetric group S3, the element x has order 3 and y has order 2. Okay, and let me just find that usual presentation. Where was it? Page 42. This was can't do anything about that right now. 1x squared y has a semicolon here. That's weird. xy, I didn't notice that on the first time I read it. X squared y. This is the usual presentation. So x has order 2. No, x has order 3, and y has order 2. Okay. In any group, the identity element is the only element of order 1. Okay. This is interesting. Right, because this is me saying that if x to the 1 is equal to 1, then obviously x is equal to 1. This is equivalent to x is equal to 1. If x to the n is never equal to 1, then x has infinite order. The matrix 101, 1, yeah, because this just keeps adding. So this would be 1. So this is an operation of adding. This is an adder. This has order 6. Is this invertible? So yeah, it looks invertible. Because it would be, its determinant is 0 minus 1. So its determinant is 1. Has order 6. That's interesting. I kind of want to, anyway. Infinite cyclic. Won't have much to say about that case. Okay. Oh boy, my leg fell asleep. Proposition 2.4.3. Let x be an element of finite order n in a group, and let k be an integer that is written as k equals nq plus r, where q and r are integers and r is in the range 0 is less than or equal to r, which is less than n. Then x to the k is equal to x to the r. Element of finite order n. Okay, I'm just going to highlight finite order n. K is equal to nq plus r. Q, it doesn't matter what q is, and r, yeah. Right, then x to the k is equal to x to the r, just by our logic above. X to the k is equal to 1 if and only if r is equal to 0. So basically if k is 0 mod q, let me just rewrite this as k is equal to 0, no, not mod q, mod n. Those are the same thing. It would also be 0 mod q, but that doesn't matter. K is equal to 0 mod n. Let d be the greatest common divisor of k and n. Then the order of x to the k is equal to n divided by d. Oh, you know, for a number theory book, I bet disquisition arithmetic by Gauss. Is there an English version of that? Let's see. None of these look like good sources. Shut up. Oh, it's the Smithsonian. Is it in Latin? It looks like it's in Latin. Yeah. So, is there an English version? Okay, well, we'll worry about that later. Let D be the greatest common divisor of k and n. Okay. All right, let me think about this. Let D be the greatest common divisor of k and n. D be the greatest common, okay. Okay, so let me reframe it as this. So I kind of have the proof in my head. So the key fact is that the LCM of n and k is equal to n times k divided by the greatest common divisor. And what it would be, so if the order of x to the k is, let's say, capital Q, okay? So x to the q k is equal to 0, or correction, is equal to 1. So it's saying that q is the smallest number, q times k, oh, yeah, so q is the smallest number such that x to the k times raised to the q power, such that this is true. Okay, well then, by necessity, q times k is equal to LCM of n and k. Okay, and then LCM of n and k divided by k divided by k, that's equal to q, which happens to also, by this formula, be n divided by d. Okay, that makes sense. Okay. One may also speak of the subgroup of a group G generated by, let me save this, generated by a subset U. This is the smallest subgroup of G that contains U, and it consists of all elements of G that can be expressed as a product of a string of elements of U and of their inverses. A subset U of G is said to generate G if every element of G is such a product. For example, we saw in 2.2.7 that the set U is equal to xy generates the symmetric group S3. The elementary matrices, generate GLN. In both of these examples, inverses aren't needed. That isn't always true. Right. An infinite cyclic group is generated by the element x, but negative powers in the... Okay. The Klein 4 group consists of those 4 matrices. Okay. This is the simplest group that is not cyclic. Any two of its elements different from the identity generate V. Any two of its elements different from the identity. I'd have to think about that some more. The Quaternion Group H is another example of a small group. It consists of plus or minus 1, plus or minus 1. Okay, yeah, the quaternions I kind of know. I know that these adjoin the key to rationals. That's what I'm more familiar with. These can be obtained by the I don't know those Pauli matrices. Okay. Computation leads to the formulas I squared equals j squared equals k squared is equal to minus 1. Ij is equal to minus ji is equal to k. Jk equals minus kj is equal to I. Ki equals minus ik equals j. Okay. That looks good. Okay, and that's all for now. This was Abstract Algebra. I'm not sure which video, 23, 24, something like that. I'll go look. Thank you for watching. I will see you in the next video. Goodbye.